Hello everybody, I would like to present you a thesis named CNN-based predictive maintenance of generalized rotation equipment authored by Oleg, Rudenko, Oleksandr, Bezsonov, Andrzej, Szajna, and Stanislav Piskunov. Predictive maintenance is a technique that uses performance indicators of some unit to detect anomalies in its behavior. In data measured by sensors, it is possible to find unusual patterns such as growing engine vibration of high or high power consumption. Usually malfunctions are preceded by some unusual behavior of the machine. The huge amount of the existing sensors is generating a huge volume of data. Machine learning algorithms can gather and analyze patterns from the data and create models to estimate the necessary machine health metrics. This paper examines the structure of the convolutional neural network and its training methods for solving the problem of aggregate maintenance prediction in combination with the methods of converting one-dimensional data into images. The data transformation step is very important for further use of CNN. A generalized model of rotating equipment was used to evaluate the proposed approach. The data was pre-processed and transformed into images and fed into a customized classifier. The simulation results showed that the combination of CNN with the data dimensionality enhancement method outperformed traditional machine learning methods like random forest, support vector machine, and forecasting methods based on multi-layer perceptron, LSTM, and one-dimensional CNN neural networks. Let's consider our proposed method. To apply Gramian angular fields or GAF to predictive maintenance, we start by collecting data from sensors on the equipment. This data can include vibration, temperature, pressure, and other relevant signals. We then use GAF to encode this data into image-like representation, which can be further processed by CNNs. CNNs are a powerful class of deep learning models that are capable of learning complex patterns and structures in main images. In predictive maintenance, CNN can be trained to recognize specific patterns in the GAF encoded time series data, such as changes in vibration, amplitude, and/or frequency. By detecting these patterns, CNN can predict when equipment failure is likely to occur, enable maintenance personnel to take action before the failure occurs. To train the CNN, we start by splitting the data into training and validation sets. We then use the training data to train the CNN to recognize patterns in the GAF encoded time series data. Once the CNN is trained, we use the validation data to evaluate its performance and make any necessary adjustments. Once the CNN is trained and validated, it can be used to predict when equipment failure is likely to occur. This can be done by feeding the new GAF encoded time series data into the CNN and using its output to make a prediction about the equipment's health. If the CNN predicts that equipment failure is likely, maintenance personnel can take action to prevent the failure from occurring. Overall method description is presented at figure 1. This picture you see that at the input of the system we have raw signal data from sensors that measure temperature, pressure, and speed. Then this data is encoded by using GAF encoding method into images, and these images are used to train separate model for each channel. This is CNN-based neural network models. After training process is finished, these models can be used by health monitor application. It is a web-based application that uses trained CNN models to forecast system states. Conversion of one-dimensional signals into images. The Gramian angular field visualization is an effective encoding method of one-dimensional signals from sensors in the form of images. This method has been proposed by Wang and Oleg in 2015. This method has become very popular due to the fact that it allows to use of well-established convolutional neural networks for signal processing, which turn out to be much more effective than traditional methods for processing one-dimensional signals. Converting one-dimensional signals to images is one option for data dimensionality enhancement, and it transitions from 1D data to 2D or even 3D. Dimensionalization is an important step when using CNN models. The GAF method uses a matrix based on polar coordinates to encode time series into an images since they have the ability to store information about temporal correlation unlike Cartesian coordinates. The algorithm for converting signals to GAF images contains the following steps. First step is when initial time series is normalized and uses reduced values in the interval from -1 to 1, according to the equation 1. The second step in building time series using the GAF method is to present normalized time series in polar coordinates, which are calculated by finding the angular cosine for each normalized value at the time step, represented as a radius using the expressions 2 and 3. And finally, after obtaining the polar coordinates for each value of the time series, the trigonometric sum is calculated to find the spatial correlation between the polar points as follows, as it presented at the bottom of the slide. Figure 2 shows a graphical representation of the conversion of time series to GAF images. So at the beginning we have just a regular time series, then it is converted to polar coordinates, and finally it is represented and encoded by into images. Convolutional neural networks. Initially, the structure of convolutional neural network was created taking into account the structural features of some parts of the human brain responsible for vision. The development of such networks is based on three mechanisms: local perception, formation of layers in the form of a set of feature maps, shared weights, and subsampling. By local perception, it is meant that not the entire image, but only some part of it comes to the input of the neuron. This allows to save the configuration of the image when moving from layer to layer. The idea of shared weights implies that a small set of weights is applied to a large number of links. The CNN consists of layers of convolutional subsampling and layers of fully connected neural networks. Each convolutional layer is followed by a subsampling layer or computational layer, which perform image dimension reduction by local average of the neuron output values as it is presented at the figure 3. So the CNN is built by alternating layers of convolutional and subsampling. At the output of the network, several layers of a fully connected neural network are usually installed, at the input of which finite feature maps are fed. Each neuron of this layer is a perceptron that has a non-linear activation function. In this work also we considered procedures of training convolutional neural networks that can be written as described by formulas 4 and 5. Those is a matrix version of the Kachmash or Widrow-Hove procedure. To increase the computational stability of the algorithm, they can be modified by introducing regularization parameters into them, like it is described in formula 6 and 7. And now we will talk about some numerical experiments performed in this work. All experiments were performed with using rotating machine emulator for generating needed data. The practical application of maintenance solution for complex systems is associated with the presence of a complex infrastructure for remote monitoring of the state of a given system. The quality of forecasting directly depends on the availability of significant amounts of telemetry and service records to failure, on the basis of which it is possible to build models of system degradation. In this case, failure prediction can be made both on the basis of historical and newly collected data. It should be noted that for more efficient modeling of a real system, it is necessary to take into account the change in the parameters of a real system over time. To do this, it's possible by using equation 8. In the investigated emulator of rotating machine are also simulated weather condition, location, and some characteristics of the operator. Operating conditions undoubtedly affect the performance and life of the equipment, so they must be taken into account in predictive maintenance. Instantaneous temperature and pressure can be modified can be modeled using some function f of t presented at this slide. At figures 4 and 5, an example of generated data is given. At the pictures, there are three channels of data: temperature, pressure, and rotation speed. As it is seen from the pictures, length of time frame between critical failures varies according to formula 8. The difference in encoding different system states with GAF methods considered temperature data channels is presented at figure 5. At figure 5, it is clear seeing the difference between different system states represented by GAF images. For the purpose of testing the considered methods, about 10,000 of rotating machine cycles were emulated. For encoding data from emulated sensors into GAF images, a sliding window method was used. The size of each window was 5 minutes and delta was 1 minute. It means that each minute of the simulated time last 5 minutes of data in each data channel was encoded into 64 by 64 by 3 images. Resulting images were collected into 3 data sets: training, validation, and testing. For each data channel, a separate CNN model was trained according to the method description presented at figure 1. The overall system health can be estimated as an average of each model prediction. Experiments showed that in 93% cases, the considered method was able to predict properly approaching system failure within 30-minute time period. Accuracy of the proposed method was compared with other time series predictive solutions based on machine learning methods like random forest support vector machine and neural network methods based on multi-layer perceptron, long short-term memory, and one-dimensional CNN neural networks. Results of the comparison are presented at the table 1. In conclusion, I would like to say that encoding signals by Gremlin angular fields and further recognition by convolutional neural networks is a powerful technique for enhancing predictive maintenance. And by using GAF to encode time series data into image-like representation and processing it with CNN, we can detect complex patterns and structures in the data, enabling us to predict equipment failure with greater accuracy and efficiency. As a result, predictive maintenance can help companies reduce costs, increase productivity, and improve equipment performance, leading to better business outcomes. Simulation results on rotating machine emulator showed that in 93% cases, proposed method generates correct prediction of the incoming in 30-minute system failure. In real life, it means significant saving of resources and decreasing of overall system downtime. Thank you very much and see you.